So let's start with today's problem statement, right? So what project do we have? So the context says there are many sophisticated models people can build for solving a forecasting problem. However, they frequently stick to simple models based on average historical values, intuition, and some high-level domain-specific heuristics. Right. So, what this talks about is forecasting problem. Right. So, uh, you want to predict the value of something. Right. So, uh, simple models would be to take the average of the past. Right. So, if you want to predict any new value, the most simplistic thing that you can do is take the average of the past. Right. So that we have seen many times, how this makes sense to take the averages of the past, right? So this is a very simplistic model, or the first cut model that you can say, right? Just take the average of whatever you have seen in the past. Okay, so it's also based on intuition and some high level domain specific heuristics. So what is heuristics? So it's these are basically some rules which are specific to the domain, right? So uh, based on your understanding of the business problem or the domain, you might come up with some rules through which you will be predicting, right? So this is what is called as heuristics, right? So based on the mean, but sometimes you don't just take the mean. Along with the mean, you will have some own rules, right? So if the mean is greater than this, I will add 50 to it. So something like that, based on your business understanding. Okay, so there are these simple models, right? So this approach may be precise enough for the problem at hand, but there are alternatives that can add more information to the prediction with a reasonable amount of additional effort. Okay, so we will be talking about one such alternative today, right? So one approach that can produce a better understanding of the range of potential outcomes and help avoid the flaw of averages is a Monte Carlo simulation. So let's see how we can use Monte Carlo simulation methods to predict the range of potential values for a sales compensation budget. Okay. So, so what comes to your mind when you hear the word simulation? Can you write in chat privately? Okay. Okay. Mm-hmm. Everyone, please write in chat what comes to your mind when you hear the word simulation. Okay, so I guess all of you are aware of this concept, right? So basically, we are trying to mimic a real world situation, right? So uh, we are trying to generate the reality artificially, right? So uh, yeah, so I've got a lot of uh, definitions. All of them seem to be different and seem to be correct, right? So basically you're doing some repetitive process that we do for some time period. Okay. Okay, simulation means experimentation on computer, right? Imitation of a process, multiple scenarios handling. Okay, so yeah, all of these things are somehow in parts true about simulation, right? So so today's problem, let's see today's problem. Okay. Okay. So we want to predict how much money we should budget for sales commissions for the next year. Okay. So how many people are from sales background? Any connection with sales systems? Anyone? So yeah. So yeah, there are few. So you might be aware of uh, these things, right? So to induce a sale, okay, we have to provide commissions to the salesperson, right? Or incentives to the salesperson, right? So uh, generally in sales, what happens is that um, of course you will give the employee a monthly salary, right? The salesperson will give a monthly salary, but that will not prompt him to or induce him to make more sales or achieve his targets, right? Whatever targets you have given him, right? So to sell some product or a service, right? So if you top that up with incentives, which will be a percentage of the actual sales that he has made, right? That will drive him more to do his work and achieve the targets rather than just salary, right? So that's why incentives are very important in sales, right? So uh, in our problem statement today, we want to predict how much money we should budget for sales commissions for the next year. Okay. So there are is a team which is the sales force, right? So there is a team of salespersons, and all of them will sell products uh, worth some amount, right? So based on that amount you have to give sales commissions, right? So you want to predict how much money you should set aside or budget for the sales commissions next year. Okay. For that, what do we have? We have a defined formula for calculating commissions, and we have we likely have some experience with previous year's commissions payments. Okay. This problem is important from a business perspective. Sales commissions can be large selling expense, and it is important to plan appropriately for this expense. In this example, the sample sales commission would look like this for a 5% sales work sales force. So you can see this chart which is given. So this is the sales representative ID. Okay, so 5 persons are there, 5 representatives, and they were given these targets. Okay, and this is the actual sales that they made. Okay, so this was the target that they were given, and this is the actual sales that they made. Okay. uh, so percent to plan. So as some of you might know what is percent to plan. So percent to plan is um, basically what percentage of the sales target did you achieve, right? So this guy, first guy, had a sales target of 100K dollars, and he sold for he made actual sales of 105K dollars. So percentage to plan is 105%, because the plan was this, right? But he has achieved this much. So percentage to planned targets is this much, right? So this is what we call it percent to plan. Okay. So second guy made did not achieve or even go close to the target. So 200K dollars was the target and achieved 140K dollars. So 70% is what uh, he made, right? So he achieved. And based on this percent to plan, we have a formula to calculate the commission rate. Okay. So of course, you want to give more commissions, more percentage of commissions to people who are achieving or overachieving their targets, right? So the commission rate is dependent on what percentage you achieve. Okay. So this is how it looks like. And then final commission amount is nothing but your actual sales into the commission rate, right? uh, Actual sales into the commission rate will be your commission amount. Okay, so which is written here, commission amount is equal to actual sales into commission rate. So the commission rate is based on this percent to plan table. Okay, so as I said, right, so 0 to 90%, you'll get 2% commission rate. Okay, 91 to 99%, 3% commission rate. And greater than 100%, basically you have overachieved your targets, then you will get 4% commission rate. Okay, so this is quite intuitive, as in this is how it should be, right? So the people who are overachieving their targets, that is their percentage to plan is greater than 100, they should be given more incentives, and this is how the table is constructed. Now, so if you now want to calculate, let's say for these 5 persons for the next year, what will be their commission amount? Okay, what would you do? Right, so you are not given a computer, nothing else, right? So you just want to have these, uh, you want to predict this number. So this is for the, let's say the current year. For the next year, you want to predict this amount, right? So this is nothing but the total of all the commission amounts. Basically, the budget that you want to set aside for commissions. So what will you do? The first thing, next year you have to predict this, right? So for the next year, you have to predict this amount. What is the best estimate that you have based on just this data? So next year you want to predict the commission amount, total commission amount, right? Which is 38.2K for this year. So the same value you have to come up with, right? So similar value you have to come up with for the next year. So what is the first very naive solution that you can have for this? Yeah, so the same budget would be the most naive solution, right? So you'll just say that, okay, next year also 38.2K will be my commission amount, right? So this is the next thing that you can do, right? Uh, uh, what is the next best solution that you can have? Okay, so the next best solution. So then you went with this amount 38.2K to the finance team, no, and they rejected and said that you need to, you know, come up with a better estimate. This is just this year's estimate. They caught you. So then what number will you quote? So you can do something like, first thing is, you want to obviously, you'll want to have a sense of what the sales target will look like for the next year, right? And then probably you'll take some commission, average commission rate, and tell them that this multiplied with this is giving me this value, right? So something like that, right? So sales target, you'll say that, okay, the sales target uh, can have, you know, somewhat greater targets based on the company growth or whatever is the next year plan. So some you can induce some different values here, right? Okay, so the first cut is what you can do is, you know, induce some set of different values here, right? Take the average commission rate, right? uh, take sorry commission rate will be fixed, right? So commission rate is fixed, but let's say the commission rate is fixed, so you will probably take different percentages to plan, right? So this you can set randomly, and these things also you can set randomly, and then you can just uh, calculate the commission amount, right? So set these randomly, okay? So whatever your intuition says, right? So the first intuition that I will have is that percentage to plan will be basically somewhere in between 60 to 150%, right? Something like that. So this is the intuition that I'm getting from this data. So I'll take random values of these, right? So, and we'll take random values of these and then multiply. Okay. So, okay. So this is again, no, this we are doing just for 5 sales representatives, right? What if you have data 500 sales representatives, right? So in that case, you cannot go with naive methods, right? There are more chances of you going wrong, right? So uh, okay, so when I say I want to take random values of sales target, what would be a good way to pick those random values for sales targets for each representative? So when I say that I want to take random values, okay, of this sales target, so for sales representative 1, or for all the persons, right? So 100, 200, 75, 400, 500, these are the sales targets. I want to take random values of this sales target. So uh, what should I do, right? So you have studied a lot of statistics uh, this week, right? So when I want to take random values, what is the first thing that I should look at, or how should I pick those random values? Okay, so I need to generate. Let's say there are 500 representatives. I need to generate 500 random values. So what is the best way to generate 500 random values for sales target? So yeah, so Monica says we can take random value between 100 to $500. So you're basically saying uniform distribution, right? So uh, in between 100 to 500, you'll take uh, all the values, right? So okay, so you'll randomly choose any value between 100 to 500, which is like a uniform distribution. Okay, so Devashi says Z into 100K. Okay, so Z score is what he is suggesting. But then again, Z is what, right? So how will you choose Z randomly? Uh, okay, so let's move forward and see. So now that we have covered the problem at a high level, we can discuss how Monte Carlo analysis might be a useful tool for predicting commissions expenses for the next year. At its simplest level, a Monte Carlo analysis or simulation involves running many scenarios with different random inputs and summarizing the distribution of the results, right? So the very naive result, as someone suggested, is just taking this value and predicting for the next year, right? So you're just saying 38.2K is the prediction for next year. But then if you want to run multiple scenarios with multiple inputs, in that case, you'll get many such commission amounts, right? So let's say I run one scenario where I generated this sales target randomly for all the 500. I generated the percentage to plan randomly. Okay, so I generated random values for this. For the whole data frame, I generated 500 random values here, 500 random values here. Corresponding to these numbers, I get the commission rate. I multiplied this with the actual sales to get the commission amount. Okay, and then I will get one number, right? So if I do one iteration or one simulation, right, taking 500 random values, I'll eventually land up with one number. Okay, so basically this is what it is suggesting, that involves running many scenarios. So instead of doing it only once, I want to do it again and again and generate many scenarios. You understand this point, right? So why would only one set not be important? Because it will be totally biased, right? So there might be a situation wherein you have generated those random values, it comes on the higher end, right? So to make sure that your results are making sense, you have to run many iterations, right? So generate two random values for this, generate random values for this, get this amount. Again, do this, and generate the amount. And this way, you will get a whole lot of commission amount values, right? And the commission amount values that you will get, right? So let's say you did 1,000 iterations, you got 1,000 such values. Then those 1,000 values will say something which will be very close to what will happen actually. Why? Because you have captured all the various scenarios, right? Generating basically random values for, let's say, 1,000 scenarios. You have covered all such scenarios that might happen, almost all such scenarios, right? So, okay, so that is what it is saying. Running many scenarios with different random inputs and then summarizing the distribution of the results. So this is the result. You will summarize the distribution of the results. Okay. So yeah, so basically now before moving forward, I want to uh, induce a term which is called sample. Okay, so you have not been learning about this term particularly in technical terms, right? So this week whatever you have learned is descriptive statistics, right? So whatever you have learned was theoretical, and it did not involve any sampling or anything. So everything was based on population. Okay, so just try to remember this term, population, right? So you were basically when you are talking about distributions, so those were very ideal curves and defined by very ideal equations, right? So normal distribution, you had a fixed equation. Okay, so we said that IQs of students could be modeled through a normal distribution. So when we say that, that means that uh, if we take the entire population, right? So entire IQs that are possible, in the whole world or universe, right? So those IQs will, uh, you know, that population will have that kind of a ideal curve. Okay, so if you plot the IQs of all such people, you will land up with that kind of a normal distribution curve. That is what we uh, say, or that is what we theoretically say, right? So those are all defined for population. So there are these two terms. One is population and one is sample. Okay, so what is the population? It basically has all sort of information, right? But what is the problem with population? It's uh, problem is you can never actually measure the statistics or the values for the entire population. You can never do that. Okay, so that's why there are some methods called sampling methods or samples, right? So from a defined population, so whenever I'm talking about IQ of students, so basically the my population is the uh, IQ of students across the world. Okay, so whenever I define my population as IQ of students in India, so that becomes my population. Okay, so when once we have defined a population, we will take a sample from that to basically do our calculations, right? So let's say I want to have a sense of the IQ of students in India, so I will take a sample from India. Okay, so probably there are many sampling techniques, but you'll probably take, let's say, sample of 10,000 students, right? So from that 10,000 students, if you plot those, right, so you'll get a histogram, right? So if you plot the IQs in a group distribution table, you will get a histogram. Okay, so this histogram will look more or less like a normal distribution. right? So when this looks like a more or less like a normal distribution, you then conclude about the population. You then say that since this sample which is taken from the population looks more or less like a normal distribution, I can say that theoretically the population follows a normal distribution with certain mean and standard deviation, right? So from the sample you can calculate the mean and standard deviation, right? That will be called the sample mean and the sample standard deviation, right? But from these two values, from the sample mean, you can conclude about the population mean. Okay, so see, you saw that the sample mean IQ is 140, right? So then you can say that the population mean will also be around 140, right? Because that is the best estimate that you can have of the population mean. The population mean itself cannot be measured at any point, right? So it is very difficult to measure for the whole population. You just define a population, take a sample from that, and then do some analysis and try to see what distribution the sample follows. And then you conclude that, okay, since the sample follows this kind of a distribution, right? My original uh, original population will also follow this type of distribution, but it will be more uniform, and it will look like a theoretical curve, right? So theoretically the normal distribution was very smooth, as you saw, right? So it's a very smooth curve, but uh, when you see from a sample it will not be that smooth, right? So your histogram will have uh, of course it will have some peak in the middle, but maybe there will be some edges, right? Where your curve will not be that smooth, because the smoothness of the curve, because in theory it is derived from an equation, right? And that's why it is bound to be smooth. But when you are collecting real values, right, what you are essentially doing is you are just plotting them, and you see a curve which seems like a normal distribution, right? So there is a peak in the middle, there are, then the values gradually decrease on either sides of the mean, right? So this is the characteristic of a normal distribution, and this is what you see when you plot the sample, right? So I hope population and sample is clear in some sense. Of course this will again be discussed when you study inferential statistics, right? So this week what we have studied uh, is called descriptive statistics, because you are basically describing whatever the population characteristics and everything, right? Now from the next week onwards you will be studying inferential statistics, wherein you will infer something about the population just from the sample, right? Make sense? So you will not be given the luxury to have, the what the population distribution is, what is the equation of the population, but you will be given a sample through which you have to conclude what are the properties of the population that the sample has come from, right? So you'll basically infer some conclusions about the population from the sample. Okay, so I hope this part is clear. If this part is clear, what is a sample and a population, inferential and descriptive statistics difference, you can write yes if this part is clear. If someone has any difficulties in any topic. So okay, so I think this was a fairly simple concept, right? So okay, so coming back to the problem, now again we so what I was saying is that here I was always saying that we have to simulate two random variables. Okay, okay. So then we were always saying that we have to simulate two input variables. So why I was saying that is because, so I will not directly simulate, I will not directly, take random values of actual sales, but what I will do is that this sales target is what I will take, right? So uh, this is what is expected to remain constant throughout the years, right? The sales target in some sense is expected to remain constant. So this distribution is expected to remain constant throughout the years, and not this part, right? So actual sales, you actually don't know what will happen, right? So this actual sales is nothing, is you cannot say about this. Okay, so that's why we will try to simulate or take in different random inputs for this, multiply that with the generated random numbers of percentage to plan, right? And we will multiply this with this to get this. Okay, makes sense? So basically sales target into percentage of plan will give my actual sales. Okay, so I will simulate this and try to get this actual sales. And once I get these actual sales, of course commission rate is dependent on percentage to plan. Okay, so I will multiply actual sales with commission rate to get the commission amount. Okay, so you get why I am not directly taking the random values for actual sales, but instead I am doing sales target, uh, taking sales target randomly, taking percentage to plan randomly, and getting the actual sales from there, multiplying these two. Okay. Okay, so there are two components to running a Monte Carlo simulation. One is the equation that you want to evaluate, right? Which is basically this, right? So commission amount is equal to actual sales into commission rate, and the random variables for the input. So I have to identify the input. So these are my two inputs: percentage to plan and sales target. This will be my two inputs to the model, right? And based on this, all these things will be calculated, right? So we have already described the equation above. Now we need to think about how to populate the random variables. One simple approach would be to take a random number between 0 and 200%, representing our intuition about commission rates. Okay, so this can be your one uh, way to think about it, right? So one way to, so first we are dealing with percentage to plan. Okay, so we will be generating random values for this. So it says that we can take random numbers between 0% and 200%. Okay, so you can take any sort of random values but and take a uniform distribution, right? So let's say 60% to 150%, that is also a good estimate, or 50 to 100. So 0 to 100 seems to be fair, 200 seems to be fair, because some people will not achieve anything at all, right? So okay, so this is the type of uh, random variables that you can generate for percentage to plan. Okay, however, because we pay commissions every year, we understand our problem in a little more detail, and we can use that prior knowledge to build a more accurate model. Because we have paid out commissions for several years, we can look at the typical historical distribution of percent to target. So this is how what you will seek for, right? So the past data is there. Okay, so the past data of all these numbers, let's say you have, you know, thousands of representatives, and you know their percentage to plan, whatever they have achieved over the past few years, right? So the first thing that you will do is use, you know, SNS or matplotlib to just plot this percentage to target, right? So once you plot it, many things will be clear, right? So this is the first EDA, or this is the first analysis that you will be doing, of course, right? Since you are given the luxury of having past data, you will try to plot the distribution, okay, and see what has happened over the years. So from this chart, from this histogram, what can you conclude? So can you start concluding things about percentage to target? So basically, this is the percentage to target that people have achieved. So no, majority people have achieved 100% targets. Okay, in the past, some people have achieved 70, some have achieved 30. So start concluding. Okay, everyone start concluding. Okay, so what does this distribution look like? Whatever you have studied this week, right? So does this resemble any of the distributions? Want answers from everyone. So does this uh, resemble any of the distributions that you have learned? Okay. Yeah, so I have got many answers, some correct, right? So this is a typical case of a normal distribution, right? So resembles a normal distribution. Okay. So resembles a normal distribution. What do I mean by that? If you remember the characteristics of a normal distribution, right? So there was a peak at the top, at in the middle. It was a symmetric. It was kind of a symmetric distribution, right? So um, this is the property of normal distribution. It looks like a bell shaped curve. Okay. And the tails, gradually fade out towards the ends, right? And it kind of looks like this, right? So uh, yeah, so we know this is how the normal distribution looks like, right? So kind of resembles that. Okay. So now you will say, so some of you might say that, okay, I have this histogram, where is that continuity? How can I say that this is a normal distribution? So that is, defined for, it will be a single line, right? So how can this be? So this is looks like a, uh, discrete distribution, right? So we have plotted for some particular numbers, but just uh, this is where the concept of population and sample comes in, right? So we are saying that this is not a normal distribution, but this resembles a normal distribution. When we say that, that means if I take if the population is, let's say, all the cells representatives over all the years, okay, so this is just a sample of that, right? So this is just historical percentage to target, but percentage to target can be thought of as following a normal distribution in the population, right? So if you theoretically say that percentage to target follows a normal distribution, this sample is basically just supporting that fact, right? So in a normal distribution, if you say that this comes from a normal distribution with a mean 100, okay, the population has a mean of 100, that is basically supported by this sample. Or saying about it in a reverse manner, we can say that since the mean of this sample lies somewhere around 100, we can say that the population of the population will actually have a mean of 100, right? So okay, so we can say that since the sample is behaving in this way and it kind of seems like a normal distribution, okay, that's why we can say that the population will eventually have a mean of 100. This is the best we can conclude about the population, right? So so there are two unknown parameters in a population, right? So in a normal distribution, what do you have? You have two unknown parameters. One is the mu and another is the sigma, which is the standard deviation, right? So if you want to describe totally the population of this percentage to target variable, okay, you need to get two values from the sample itself, correct? So the first value which I see is very obvious is that saying that the mean is 100. right? So here is your 100%, right? So you can see that this is kind of the mean. We can look at this graph and figure that out, right? So you can figure that out, that the mean is 100. Okay, and we can say that the population mu is equal to 100. Okay, we are very close to the actual population, right? So if we somehow find the standard deviation from this graph or this sample, we will be able to conclude, we will be able to model the entire distribution, right? So we will be able to um, define the population, right? And then all sort of calculations can be done. Okay, so you can calculate what is the probability that a certain salesperson will have a percentage to target less than 80. So this is the percentage that you can calculate percentage greater than 120 and so on. So what is the best way to get the standard deviation from this sample? Just by looking at this graph, just by looking at this graph and whatever you have studied of the normal distribution. So normal distribution was talked about in detail, right? So just think about the standard deviation and how that looks like, right? So you were given many intuitions. Okay, so what can you conclude just by looking at this graph about the standard deviation of the normal population that this sample is taken from? Standard deviation, anyone? uh, okay, so you can see the spread, right? So just remember what you have learned, right? So what did you see in normal distribution, right? So uh, I told you, 99 percentage of all the values lie between mu minus 3 sigma and mu plus 3 sigma, right? And that's how 6 sigma was the total spread, right? So almost all the observations lie in the range of 6 sigma, right? So if you remember this fact, that if this is mu, right? So the ends, mostly the mu minus 3 sigma and mu plus 3 sigma, two ends will have uh, you know will have, okay, okay, okay. So yeah, so many of you have were able to figure out that sigma should be 10 for this, because um, here you can see almost all the values lie between 70 and 130. Okay, so basically, if you think about it that way, if you think about it that way, uh, this is mu minus 3 sigma and this is mu plus 3 sigma, more or less, right? So we're just estimating the uh, mean and standard deviation of the population from the sample. So we are bound to have errors, right? But what is the best estimate that we can have from just by looking at this image? Okay, so we are also not given the actual data of this. Otherwise, you could have just calculated the standard deviation and mean just from the sample, right? So if you are given values like this, 70, 80, 80, 85, 90, and so on, so the entire sample data was given, you could have just calculated the mean and standard deviation from there. Okay, But just looking at this graph and the characteristics of the normal population that we know of, right? So we know that in the center there is mu, and we have 3 sigma, mu plus 3 sigma and mu minus 3 sigma, in which, in the this is the range in which almost all the population lies. And you see, the ends of the population, right? So the ends will not, uh, so this is how your normal distribution will look like, right? So almost, no, all the values lie between these two ends, right? So of course this is never going to touch the x-axis, the normal distribution, right? That will never touch it. But 99.9% values lie between mu minus 3 sigma and mu plus 3 sigma. This is a very important property which you should remember, right? So since the spread is given, right, the standard deviation is given, how can you intuitively infer from a graph? So this will come in very handy. Okay, so this is your mu, and this is your mu plus 3 sigma. Of course, this will be mu plus sigma, something like that. Somewhere around here it will be mu plus 2 sigma. So what is the value of sigma now? Can you calculate from here? So what is the value of sigma? Okay, so everyone, what is the value of sigma now? So it's 10, right? So it's 10 because you have, uh, so this distribution looks like a normal distribution with a mean of 100% and a standard deviation of 10%. This insight is useful because we can model our input variable distribution so that it is similar to our real world experience, right? So this insight is useful. Okay, so let's define those variables as well as the number of sales representatives and simulations we are modeling. Okay, so now, so what is the next step now? So you have defined the population. So you have made some harsh conclusions about the population, right? So you say that percentage to target this particular value, this particular random variable follows a normal distribution with a mean of 100 and a standard deviation of 10. This is what a word, this is a verdict that you have, this is a conclusion that you have made. Okay, now coming back to the problem statement. So how will you generate values for this? Now how will you generate percentage to plan values from this information? So you know that how this population varies. What is the property of this variable? Okay, you know this fact. Now you want to generate 500 random values. Okay, so what will you do? So what is the idea? Yeah, so basically you have to uh, take samples from the population, right? Now you have to, since you have defined the population, okay, you can now take random samples from the population. Okay, so okay, okay, right. So you can take random numbers from the population. Okay, uh, yeah. So whenever we say that from the population we will sample, some observations. What do we mean by that? Can you say what do you mean by that, right? So let's say I have a normal distribution and what I want to take samples from that. What do you mean by that? So we are picking random numbers from the distribution. That is okay, but like uh, take this example, right? So we have a normal distribution with 100 and 10% as your 10 as your standard deviation and mean as your 100. So when you start picking samples from this normal distribution, right? So what will be the characteristics of those numbers that you pick randomly? So can I say that, between 70 to 130, you will get, if I, let's say, divide this into 6 chunks, okay, try to understand this fact. 70 to 80, 80 to 90, 90 to 100. So this is the 6 buckets that I define, okay. So 1, 2, 3, 4, 5, 6. 6 buckets is what I am defining. Now I start taking samples from the population. Uh, what does that mean? Will I see equal number of observations in each of these buckets? Let's say I take 600 samples from this population. Okay. So will I see 100 numbers here, 100 numbers here, 100, 100, 100 here? This will this be how the distribution looks like? Yes. So I start picking samples from the population. Will I get 100? I pick 600 samples. Will I get 100 samples in each of these buckets? No, right? So let's try to see. Okay. Uh, okay. So let's say you have this kind of a distribution. Okay. So this looks almost like a normal distribution. Okay. So this is, let's say you have this kind of a uh, distribution. Okay. So now you start sampling data from this. So what do you mean by sampling? So here, this is the x-axis, right? So this is the x-axis wherein you have all sort of values in this line. Okay. Now, and this is the y-axis, right? So this height or this fx value, what does this give? It gives what is the density, that what is the probability, that this x value will be chosen. Not that will not give you directly the probability, but it will give you how likely uh, this value will be chosen. Or if I take, uh, an x value here, the fx value here is very less, right? So if I take a x value here, the fx value here corresponding to this will be very less, right, as compared to here, right? So here the fx value will be more, correct? So this value of x, let's say this is x1, this is x2, right? So if I pick a random sample from this population, what I am essentially saying is that I want to pick a value of x, nothing else, right? So I want to pick a value of x, but since this these type of values are more likely to get picked than these, right? Because this the probability of this getting picked is very low because of the value of fx, right? So these numbers are not that dense. Okay, so um, just yeah, so just clear this up. Okay, so you get an intuition about how these values, these type of x values are more likely to be picked rather than these values. Okay, so now let's say I start sampling. Okay, so sample, so from this value I got one sample. So it came out randomly from this point. So this was the value of x that came out. Okay, then this value came out. Okay, so and then this value came out. Okay, so this way you can keep on sampling. Okay, so you can keep on sampling like this. Okay, so what you see is that in the long run, okay, in the long run, what you will start seeing is that these numbers have a high chance of getting picked in the long run. Okay, so as you can see, these numbers will have a high chance of getting picked in the long run, and these sort of x values will have a very low chance. You see 1%, 1%. Neither of the middle ones have 1% distribution, right? So you can see how this comes up to this, right? So as you can see, right, so if you take enough samples, that is if you take infinite number of samples from this population, okay, it will resemble your original population. Okay, so you can see how this plot looks like. So this is the theoretical numbers that you should have got, right? So this is the theoretical, this is just the same distribution as this. Okay, so theoretically you should have got maximum number here, right? This bar should have touched here. Okay, theoretically this is how it should have been looked, right? So the gaps that you see here are due to we not taking enough samples. So if we take infinite number of samples, your gaps will get closer and closer. Okay, so this is I hope you are able to get as to what sampling actually means. So how do we sample from a population? Okay, and what is the characteristics? I hope you have this part is clear. Okay, so moving on. So now we have this population. So we want to generate 500 random values. So I'm just saying that, okay, the number of sales representatives that I have is 500. So I need to generate 500 such numbers corresponding to different sales representatives, right? So I want to pick, so this is, if this is my population 100 with a mean of 100 and a standard deviation of 10, right? So I want to pick 500 such numbers. Okay, so so as to be very close to what I have seen in the population, right? So I want to pick 500 numbers for these sales representatives, right? So I have so I'll just write the numbers. Okay, so I have a mean of 1. So I'm not taking 100 and 10. I'm just taking 1 and 0.1. So basically I'm taking the ratio. Okay, so 100% means 1, 10% means 0.1. So 1 and 0.1 are my standard deviations, and number of representatives is 500, right? So with these numbers, I want to generate 500 random numbers from from a normal distribution with this mean and this standard deviation. So there is a So start writing this code in your notebook. So you have this norm function, right? So which you can use. Okay, so there is norm.rvs. Okay, so you have used norm.cdf to get the to get the to get the numbers, right? So you have used norm.cdf. So today we will be using norm.rvs. Okay, so this takes three parameters. Okay, and it basically generates, random variables from the sample, right? So whatever we were doing here, we were sampling from this distribution. So this is what it does. This is what this function does. Okay, so norm.rvs. Okay, you just provide the mean, the standard deviation, and how many numbers you want to generate. So I want to generate 500 numbers corresponding to the 500 representatives. Okay, and I want to round all those numbers to 2. Okay, so as to be uh, so as to be able to visualize it. Okay, so this is the percentage to target numbers that I get. So I'll just run this. Okay, so I generated 500 numbers. Okay, with this mean and standard deviation. So just try to write this code in your browser, in your notebook as well. Okay, so I generated 500 numbers. Okay, so this is how it looks like, right? So I plotted the distribution plot of those 500 numbers. So as we said, right, so since it is a normal distribution, uh, I picked 500 numbers. It kind of shows the distribution which is close to a normal distribution, right? So this is what I was able to do. So to again uh, emphasis on that fact that if we take enough samples, we will get close to the normal distribution. So let's say I take 10 samples, so it will look something like this, very abrupt. Okay, so as and when you keep on increasing the number of samples, okay, it will go more and more closer to a normal distribution. Okay, so you can see how this is getting more closer to a normal distribution. See, uh, with 1 lakh points, it's almost giving a normal distribution. Okay, so you see how this is happening. Okay, so the more and more samples you take, right, the more closer you will get to the actual population. Okay, so for our case, we are generating 500 numbers of this population. Okay, so we have generated 500 numbers. Okay, so what is the next thing? So what is the next thing? So next thing is, let's say we just want to visualize what sort of numbers we are getting. So you can see we are getting all sort of numbers. So this the first representative has achieved 94%, second has achieved 95%, and so on, right? So some people have overachieved their targets 1.12, right? 112%, 114%, and so on. But the distribution looks like this. Like majority will have achieved only 100%. Very few will have achieved very low numbers, right? And very few people will have achieved very high numbers. Okay. So you can see the distribution, right? So this is how it looks like. Okay, when I am taking these type of random samples, okay, uh, can you say that could I have gotten a number which is, let's say, minus 200? So I have a mean of 1 and 0.1. Okay, so um, could I have got a number of minus 200? could this PCT target at any point give me a number which is minus 200? Is it possible? Can you write? Is it possible to get a number minus 200? Right? So you got X values as 1, 0.97, 0.91, 0.83. You got all sort of values. Uh, could I have seen a number minus 200 at any point? Many people are writing no. Why? So just think about this line of code. Okay. So you have a mean is what you have provided a standard deviation. Okay, and then you are saying it to generate random numbers with so this is your normal distribution, you want it to generate random numbers. Okay, so will you get minus 200 or plus 200 or plus 500 such type of numbers? Will you get at any point? Let's say I keep on iterating and keep on, let's say I keep on generating random numbers. Will I get such values? 500, 1000, minus 200, minus 500, such values? So those who are saying no, right? So is it a strict no or is it almost no? Right? So why will we not get? That is because it's very unlikely. The probability that a number less than, let's say, mu minus 3 sigma, what is the probability that you will get a number less than 0.7? As you know, it's 0.001, right? So you say that 99.9% of the population will have a value greater than mu plus 3 sigma, right? So it will all lie in greater than this region, right? So 99.9% of values will be greater than minus zero point 0.7, or sorry, zero point 0.7, correct? So you're saying only 0.01% values will be less than zero point 0.7, right? So so theoretically you can get all sort of numbers, minus 1 lakh, minus 2 lakh, minus 200, minus 500, but practically it's very unlikely that you will hit those numbers. Okay, so practically it's very unlikely that you will hit those numbers. Theoretically, as you know, right, so it can take values till minus infinity, correct? So uh, this can uh, no one is stopping this function to return those sort of numbers, but it's very unlikely that you will encounter those numbers. That's it. Okay, so I have generated my 500 numbers corresponding to percentage to target. Now what is the next variable that I have now? So before moving further, I wanted to discuss one more method of how you could generate random variables. Okay, so this is uh, so you are let's say you are only to use uniform uh, function. Okay, so you are not given the norm, let's say the norm functionality. Okay, so just using uniform, can you generate normal random variables? Can you think on those lines on how we can generate uh, normally distributed samples with a mean and standard deviation if we are not given this function norm? Can we use uniform to somehow generate this type of a distribution? Think for a minute in that regard. So just using normal So just using uniform, can we generate normal random variables? Is there some way through which you can generate normal random variables? Uh, you know, uh, so I'm just saying you non.rvs is what you are restricted to stop. You can use any other non-dot function that you have studied uh, over this week. So non.rvs is restricted. So you cannot directly generate random variables from norm, but you are free to use other methods uh, on norm to generate. Okay, so use norm, uniform and norm together, but not directly this RVS. Can you think? Can you think of any entity? So what does uniform do? Right. So uniform generates a uniform set of values between two numbers. Right. So let's say I want to generate uniform numbers between 0 and 1. Okay. So let's say I generate uniform numbers between 0 and 1. So is there any entity or any function that you have encountered which takes a value between 0 and 1 only? So probability density function, CDF, PDF, anything that you have studied which takes a value between 0 and 1 only? Okay. So yeah, so some of you are saying that CDF, right? So CDF, as you know, cumulative distribution function always takes a value between 0 and 1. Correct? So whatever is the function, okay, whatever be the distribution, your CDF, your PDF will have different values for different function, but for the CDF you can definitely say that it will lie between 0 and 1, right? That is what we have seen, right? So by definition it is built that way, right? So at the maximum value of the range you will always have a value of 1, and at the minimum you will have a 0, right? So CDF is something which always has a value between 0 and 1. Okay, so I just want to emphasize on that fact. So if you, let's say, somehow generate the CDF values for a particular distribution, can you generate the original random value for which that particular number is the CDF? Right, so you have learned this thing. Okay, so you have learned this particular thing given. So yeah, PPF, you are correct. So you can use this PPF thing, right? So which is basically the inverse of your CDF, right? So it basically gives you the inverse of CDF. So given uh, R, get X such that P of X less than X is equal to R. So this, for this you used to use this function PPF, right? So uh, you were given this probability, right? And given this value, you wanted to, would you want to get this X value? Okay. So how did you do that? You used something called PPF, right? So given the probability, the cumulative probability, you could find the value of X, you know, uh, X corresponding to that CDF, right? So basically this is nothing but, so uh, basically, so this is nothing but the inverse of CDF, right? So this is nothing but the inverse of CDF, correct? So given the given the value of that you get from a CDF, you can get the actual value of X. So this is what this is doing, right? So now also we know that, you know, CDF will always lie between 0 and 1, correct? So if you start taking uniform values between 0 and 1 for R, the X values that you will start to generate will follow the original distribution, right? Whatever it be. correct? So let's try to use that code. Okay, so let's say I generate random values between 0 and 1, and that I called as CDFs. Okay, so I will generate the CDFs. Okay, and then what I can say is that to generate the normal values, I'll just use CDFs as my PPF. Okay, so in the PPF I will just put those values of between 0 and 1. Okay, so just to show you, CDFs is nothing but just giving me random values between 0 and 1. Okay, so you insert these values into this function ppf, right? And it will give you certain numbers corresponding to this x, right? And this x will, of course these x's will correspond to normal values, right? Because you have used the normal normals inverse function to generate the numbers x's, so it will give you normal CDF. So in this way you can actually generate uh, random numbers, right? For any population, given you are able to generate random uniform numbers. Okay, so just to emphasize on this fact, so let's say u is the random variable, so this you are able to generate, let's say. Okay, you have this CDF which is given by f of x. Okay, now so this f of x is your basically nothing but your u, right? So uh, f of x is, let's say, some function. Okay, so in case of exponential it is 1 minus e to the power minus lambda x, let's say. Okay, so take the inverse of this function. Okay, f inverse f x is equal to nothing but, so equate it to y and then make it this, just rearrange this. So this inverse of this function will give you values of x, right? So in that inverse, right, so if you equate it to, so you generate a random value from u01, right? So let's say that value is u. Okay, so you equate it to u and get the value of x. So this x value will come from a uniform distribution, or a exponential distribution, right? So this is what you are essentially doing here. Okay, so just taking a uniform value, right? And you are saying that, let's say this is 0.1. Okay, so you are saying that fx is 0.1, then what is the value of x, right? So this is how you can generate values of x which will correspond to the original population. Okay, so yeah. So yeah, I have generated again uh, 500 set of values. Okay, of course I have not used round 2. So let's say if I use round 2, it will all become similar to what we have got. So of course this and this will not be same, because we are generating random values, so every time it is generating random values, so you cannot say that these two arrays will be the same, right? So this is also one of the methods to generate random values. Okay, so now the second variable that we have, okay, the second variable that we have is actual sales target. Okay, uh, okay, so to generate the actual sales target, as we said, right? So we are not generating the actual sales. We are not generating the actual sales directly, but we are generating sales target and percentage to plan. Okay, so this is the sales target and not the actual sales. Okay, so remember that. Okay, so why are we okay, so from this curve what can you conclude? So this is the historical sales target distribution. So what can you conclude from here? So yeah, so uh, you have your sales target. So what I can say from here is that, most of the time sales target is 100K. Okay, so that is correct. Someone says that this is kind of looks like exponential distribution, right? So exponentially decreasing sales targets. Okay, so 100K is the uh, most frequent target. Okay, so that is correct. 200K is this much, 300 is this, 400 is this, and so on. Okay, so basically what is happening here is that why this is a good way to look at, why the historical sales target distribution is a good way to look at, because this shows us that sales target are set into of six buckets, and the frequency gets lower as the amount increases. So this distribution could be indicative of a very simple target setting process where individuals are bucketed into certain groups and given targets consistently based on their tenure, territory size, and or sales pipeline. Correct. So this is a predefined thing for a company, right? So the company has defined that there will be six target buckets, and I will give the employees, some employees will get 100K target, some will get 200, 300, 400, and 500. So this is a very obvious thing if you think about it. No, this denotes a real world scenario wherein the no, most of the salespeople will be given targets of the lowest value, right? And very few people will be given high values of targets, right? So probably these are very uh, high performing people, and they are managing a very large territory, right? So those type of things affect as to which person is getting which target, right? But this, of course, the lower limit will be the most frequent target, right? So everyone will be told to go and achieve these targets, right? Of course, other variations are there based on territory, tenure, and of course other factors, right? So now we want to generate random value variables from this type of a distribution. Okay, so let's say uh, this is what, this is 300, this is 100, this is 50, this is 25, this is also 25, let's say. Okay, so these are the relative frequencies. Okay, so these are the frequencies. So if let's say I want to generate 10 numbers, right? So how many numbers, if I want to generate 10 numbers from this distribution, so how many numbers will uh, on an average, how many numbers will be picked which will have a value of 100K? So I just generate 10 random numbers from this distribution. So in that distribution, out of 10, how many numbers will have this value 100K? No, 5 at least, right? So 5 at least will have 100K, right? So this is what I'm getting answers, 5, 6, 7, right? So majority will of those 10 numbers will be having this value 100K, right? So basically it will be chosen based on frequency, right? So if I select 1,000 numbers, probably this is, let's say, a curve of 1,000 numbers, so 300 or no more than 300 will have these set of values 100K as the targets, right? So again same problem, but this does not belong to a standard distribution. Okay, so wanted to emphasize on that fact, right? So does not belong to any named standard distribution. Okay, but you can say that no, the PMF, or this is a discrete kind of a distribution, right, wherein you have these discrete values. Okay, so this is one point that you want to notice, which was not the case here. So this is not the case of a discrete distribution, you can figure out from here, right? But here this is a definite case of a discrete distribution, right, wherein you have uh, only six set of value, or five set of values which the variable x can take. Okay, so only five values. Now if you want to start generating those values, you want to generate random values of these five, So you will have to define your own custom distribution. Okay, so one way to do it is through random dot choice function in numpy. Okay, so I'm writing the code, just try to write these. Okay, so what I'm doing here is that, so there were 5 buckets in the data, right? So I am writing 6 buckets. Okay, so this is close to 60%, right? So this is close to 60%. So what I am doing is that I'm writing 75k and 100k as two different, and setting their probabilities to zero point 0.3 and zero point 0.3. Okay, so that you know there's some bifurcation that I did in this 100 also. Okay, but the others I have tried to keep it nearly as per the ratio. So these are the 5 buckets that you can see here. Okay, I have included one extra bucket and then assigned these probability values to each one of them. So to make it a probability distribution, you have to make sure that all these values sum up to 1. Okay, so I have assigned 0.3 probability to this, 0.3 probability to this, zero point 0.2 to this, 0.1 to this. So how much has been covered till now? 0.9, right? And 0.05 to this, 0.05 to this. So this is the PMF that I constructed, or the probability mass function, or the distribution function that I constructed. Okay, so you remember the tables, the dice tables, right? So we assign probability that the value x will take a value of 75k. So what is that probability? 0.3, right? So this is x, this is p of x equal to x, this is x, this is p of x equal to x. Yeah, and this is probably a new notation that you are seeing. Okay, so I'm writing underscore. Okay, I could have avoided this. Okay, but I'm just writing underscore. So this is just another way which Python supports, right? So Python brags to be a user friendly language, right? So when you write in numbers, you just want to have that count of zeros separate, right? So um, when you write 75,000, you write 75 comma 1000, right? 75 comma 3 zeros, right? So to write a similar thing in Python, you have this functionality underscore, which you can use. So this is nothing but 75,000 only. Okay, so don't get confused. Yeah, so you can use np.random.choice, and you have to use this syntax. So you have to first give the values from which you need to pick. Okay, how many values you need to pick? So I'm giving it 500. Okay, and what is the probability distribution of these set of values, right? So this is the probability distribution that you mentioned. Based on this, it will pick values. Okay, so just run it. Okay, so I have got all sort of values, right? So 75,000, 200k, 75k, 400k, 500k, 100k, and so on, right? So all sort of values is what I have got, 500 set of such values. Okay, so I hope you have written this chunk of code. Okay, right? So now I think all your random numbers have been generated, right? So whatever inputs you wanted have been generated. Now just a matter of time, wherein I'll just now multiply the use the corresponding formula to get my first set of values. Okay, so basically what I want to do is, so making a data frame, right? So making a data frame wherein I have two columns, percentage to target and sales target. Okay, so these are the two values that I generated. These are the list of two values. So making a data frame out of it, and to get the actual sales, I'm just multiplying percentage to target with the sales target. Okay, so yeah, so this is how it looks like. So 500 set of random values is what I have for percentage to target. and sales target, I have 500 random values. I joined all of them together, right? Created a data frame, and sales is nothing but this is the actual sales, which is nothing but the percentage to target multiplied with the sales target. Okay. So can you just quickly write a function which will calculate, based on the percentage to target, it will calculate the commission rate. So just write a if else based function for this chart. So this is the rate schedule, right? So for percentage to targets, you will get commission rate. Okay, so I want to calculate the total commission, right? So we want that function. So can you just write a function which gives commission rate based on percentage to target? So we will be using that function and apply that on this column to get a new column called commission rate. Okay, so write a function quickly. Just use if else functionality. So I hope you are able to write this function, right? So if so, this will calculate the commission rate. So you will provide the percentage to target. Okay. So if it is less than 0.9, you will return a commission rate 2%. Less than 0.99, right? So it will return 0.03, and else it will return 0.4. Of course, you will say that between 91 and 99 it's 0.3, right? So uh, if it encounters a value which is less than 0.90, right, it will return from here, correct? It will directly come out of the loop and return from here. But if it is going till here, right, that means that it is not satisfied this condition. So automatically it's greater than zero point 0.9. So greater than 0.9 and 0.99, it's returning 0.03. I hope this function is clear. Okay. So yeah. So yeah. So now, so my commission rate will be nothing but it will be calculated by applying this function commission rate to percentage to target, right? And the commission amount you can get by just multiplying commission rate with sales, right? So now let's see what values do we have. So we have this percentage to target, sales. This commission rate is calculated based on the sales target. So just remember, these two are the input variables that were generated randomly. Okay, for 500 employees. Okay, this is the sales, which is nothing but the product of these two. Commission rate is derived from percentage to target. Okay, and commission amount is basically commission rate into actual sales, right? Commission rate into actual sales gives you commission amount. Okay, so this is how you generated your whole table. Now you have to just sum this up to get the total budget, right? So total budget is how much? DF Okay, so you got uh, so everyone will get different values because you are playing with different random numbers, but it will be in the same ballpark range. Okay, so you must be getting this type of a number. Okay, so can everyone just complete this and tell me what is the commission amount that you are getting? Okay, so just complete till this part and write the commission amount that you are getting privately. Okay, so I am getting around 2823, so around 2 million. Okay, so 2.8 million is what I'm getting. Okay, so can everyone tell me how much commission amount you are getting by doing all this? Everyone quickly complete this step. Okay, is anyone stuck at some point? Can you let me know if anyone is stuck at some point? So just calculate the commission rate function, write this function. Okay, which we will apply onto percentage to target to get the commission rate. Right, so again, commission rate into sales will give you the commission amount. Right, so straightforward. So here what we have done, we have constructed a data frame. So you can paste this line of code to calculate the data frame. Okay, so calculating the data frame, and then df sales. Okay, just have to write this product percentage to target into sales target, you'll get sales, right? And then calculate the commission. Very straightforward calculations. Okay, so so whoever has completed, so now this is for one set of values, right? So you calculated commission amount for only once, only one iteration. So you generated 500 numbers here, 500 numbers here, and calculated the commission amount only once, right? So can you loop over this entire functionality, right? So whatever we did till now, right? So copy all the codes, right, and loop over it to get, so this we calculated for once, right? So calculate it for, let's say, 1,000 iterations. Okay, so 1,000 such scenarios. So write a for loop, write all those code in between, iterate it for 1,000 loops, and calculate 1,000 such numbers. So whatever you calculated once, right, calculated this number once, right? So just write all this inside a for loop and calculate, um, 1,000, simulates 1,000 such numbers. So this is one simulation, right? So we just ran one simulation. Okay. So we simulated, we generated input values randomly for percentage to target, sales target. These were fairly straightforward, these formulas, and we calculated the sum of the commission amount. So this is for one iteration or one simulation. So run 1,000 such simulations. So so every time you run this particular code, you will get different values, right? So if I start running this code again, I will get different values, right? So see, it was 2.82 something. Now we have 2.81 something, right? So if you start calculating this over and over again, you will get all sort of numbers, like 1,000 numbers of this sort, right? So can you do that? Okay, so try to um, uh, write a for loop. Inside for loop include all these calculations, okay, and generate 1,000 such numbers. Okay, in each iteration you might want to store a few things, like what is the, so this is the commission amount sum, right? So you can have, you can calculate the sum of, so this is the actual number that you want, but you may want to, calculate other such numbers. So what is the total sales that is happening next year, right? So this is this simulation, from this number you can calculate that as well. What is the sales target that was given, total sales target? Okay, so this is also a simulated number, so you can calculate. So run 1,000 such iterations and store these values, commission amount, sales, and sales target, in a data frame. Okay, so just write the for loop here, right? So the real magic of Monte Carlo simulation is that if we run a simulation many times, we start to develop a picture, okay, of the likely distribution of the results. Okay, so uh, store three values, okay, in a data frame uh, after running the simulation. So your final data frame should look something like this. So it will have a column called the simulation number. Okay, so this will vary from 0 to 1,000, let's say 0 to 999. So I want you to run 1,000 simulations. Okay, so simulation number, and for each simulation number you will get these numbers, right? So total commission amount, total sales, okay, and total sales target. Okay, so your data frame should have 1,000 rows with each of these columns. Okay, so for each simulation you will get the total commission amount, You get the total sales and the total sales target. So after you have generated the for loop, right? So write the for loop, okay, and then in your final data frame, which will have these columns, just uh, just try to run these commands, okay. Try to run these commands, okay. So we'll describe the results and then just plot the histogram of the total commission amount. Okay, so if you are writing this for loop, right, so is your basically the simulation number, right? So you are iterating, so I will take values from 0 to 999, so every I corresponds to one simulation. Okay, so this is the simulation number. So if you are done, let me know in chat that you are able to plot this histogram. Okay. So to write this for loop, you don't have to do anything. Just copy paste all the codes that you wrote here, right? So uh, and finally store these four numbers in a data frame. So just define a data frame here. Okay. So df equal to something, this empty data frame here. Okay. With these columns, and then just paste all those codes from the top. And finally just the append whatever values you are getting, right? So append these values, whatever, right? So this will be the structure of the code. Okay. Results df. So once you are done, let me know. Hello. So yeah, I hope you're done with the data frame and you have ran this code. Okay. So I have just included all the codes which where I am generating the sales target percentage to target, and then I'll calculate the actual sales, commission rate, commission amount, and finally in the results DF I will store the commission amount, sales target, right? So I can also store one more column, okay, so which is the simulation number, as I said. So this will be nothing but I. So this is the simulation number. Okay. So 1 2000. Okay. So now I have got my all the results for each simulation, right? So now I have plotted this histogram for the commission amount. Okay. So basically, uh, if so, you go with this graph to the finance department uh, instead of going with one prediction. Okay, so instead of going with one prediction, let's say 2.8 million, you go along with this graph. So this has much more utility than just one value. Why? Because now you can say that the mean value, the mean budget that will be required next year will be somewhere around 2.85 million. Okay, so from this graph you can see that the mean will be somewhere around that value. But if the finance department asks you that I want to be 99% sure about the amount that it will not be exceeded, okay, so you can answer from this question, from this graph. Okay, so you'll say that, okay, set a value of 3.2 uh 3.2 million, and you have a 99% chance that it will not be exceeded. Correct. So it is almost like a normal distribution. 99 percentage of the values lie below 3.2 million, right? So from this graph you can say that, okay, if you want to be 99% sure that your value, your budget should not be exceeded, keep a budget of 3.2 million. Okay, so this is how this particular simulations now, like doing more and more simulations and getting a distribution of the final amount is much more helpful than getting just one prediction of the final amount. Okay, so you basically get a range or a distribution of the final result and not just one number. So this is a good way to forecast rather than coming up with one such number. So of course from this curve, right, from this histogram we can calculate if he wants that I want to get one such number, what is your best estimate, right? So your best estimate will nothing but the mean, 2.85 million, that's all, right? So but there are various other questions that can be answered from this histogram of the regarding the forecasting. Okay, so this is the use of Monte Carlo simulation. That ends the guided project session. So I hope you learned something new. So please try to submit the notebook before the next session. Okay, and yeah, so before 2 p.m. try to submit the notebook and complete the whole thing. I hope you have already completed it, right? So closing the session as of now. Anyone has any questions? No, right? So, okay. So I'll be closing the session for now. So this is all we had regarding Monte Carlo simulation and how we can, generate random values from a distribution, what population and sample mean, and so on. Okay. So I hope you learned something new today. See you in the next session, which is at 2 p.m. Okay. So goodbye.